plane 0 divided by a second order term in denominator. Now let's do the algebra. So we use the same inductor volt second and capacitor charge equation as we use in a steady state calculation, but the only difference here is that the inductor volt second or capacitor charge is not balanced over a switching cycle, or the average is not zero. Here the difference is that the average of the inductor voltage, because of the relationship between voltage and current in an inductor, gives us the variation of the current over a switching cycle. Likewise, the variation or the average of the capacitor current over a switching cycle gives us the variation of the capacitor voltage. These are basically inductor and capacitor equations. We only applied the linear operator of averaging to them. So let's say in a well, we use this. You will see later how we use this equation to derive the transfer functions. Using our naming convention, instead of using the DC component that we use in a steady state calculation, we need to use the DC component plus some small signal variation. So basically, duty cycle will be replaced with duty cycle plus small signal duty cycle. And similarly, D prime inductor current and output voltage will be replaced by DC term plus a small signal term. Now let's, using these substitutions, let's write the capacitor charge balance equation. So the average of capacitor current over one switching cycle was minus D times I load, which becomes minus capital D plus small d times I load, and D prime becomes 1 minus D minus D. And this whole term, instead of 0, becomes the value of capacitor times the variation of capacitance voltage over time. And please note that V out, which is the DC term plus AC term, in derivative can be summarized to just AC term derivative over time. And that's because the DC term is constant. So now, using this equation, we can make DC terms on both sides equal. So what DC terms we have on the left-hand side is this capital D is DC, I load is DC. So we have minus D times I load. And then 1 minus D times inductor current minus I load. These are all DC terms. And the DC terms on this side is 0. This is a time varying term. So we can say that if we use that DC term, we will get the same result as we got in steady state. Now, if we write the first order terms, so small signal variables, which is minus this is small d times I load plus 1 minus d times small IL, this is another first order term, and then minus d times inductor current minus I load is equal to C times dV out over dt. This will give us this equation. So this is a first order equation. We have one AC component in each term in this equation. And note that we have second order terms also in this equation, which is the product of the variation of duty cycle and the variation of inductor current. But since these are two small variables multiplied by each other, we neglect this term. It's a second order effect. Similarly, we can do same calculation for inductor volt second balance and equalize DC terms and first order terms. So first order terms will give us this equation. And then if we substitute the variation of inductor current, the AC component of inductor current, from one equation and use it in the first equation that comes from capacitor charge balance, we will get the ratio for duty cycle to the output voltage as Vi over d prime squared, which is the low frequency gain as we expected, a right half filling 0, and a second order term here. The only thing here is that please note that I included the load resistance instead of an ideal current source at the output of the converter to have this damping factor. So this R is basically V out divided by load current. Otherwise, if we assume that the load current is a perfect current source, we won't have this damping factor, and we'll have this non-realistic situation where the denominator on this transfer function would be just have a complex pole on the imaginary axis, and this gain would be infinity when the frequency is a square root of this value L times T over D prime. So to fix that problem, I added the damping resistance term to the transfer function, which comes from the resistive load. So now we understand our transfer function from duty cycle to the output voltage. We know the gain of the sensor, we can assume that to be 1 for now, and we know the gain of pulse width modulator. So the question is, what should be the compensator so that for a closed loop system we have good transient performance and we make sure that the closed loop is stable. So for that purpose, we use our same loop gain and phase margin and gain margin method that we use in LDOs. So let's start with the definition of the loop gain in our case. So loop gain is, we just go around the loop and multiply all gain values. So H of S is the gain of the sensor or feedback resistive divider, which is 1 in our case. GC of S is used to denote the compensator. G of M is the gain of the PWM modulator or duty cycle modulator, which is 1 over the peak of sawtooth. And then GVD is what we just calculated, the open loop transfer function from duty cycle to the output voltage. So the loop gain is product of all these 4 terms, where the last term is the most important one that we just calculated, and the compensator is our design parameter. So before designing a compensator, I start by assuming that the compensator gain is unity, and these all 3 terms are also unity. So I just plot the duty cycle to output voltage transfer function to understand how is the stability phase margin the low frequency gain. So here's the pole 0 map of this transfer function. We have one right half plane 0 and a conjugate pole, and body plot confirms the same behavior. So at the conjugate pole frequency, we have this magnitude peaking, and then we have a very sharp drop off of the gain, but then the drop off becomes weaker because of the effect of right half plane 0. In terms of phase, we have 180 phase drop at this conjugate pole frequency. The right half plane 0 adds an additional 90-degree phase margin. So the total phase drop. So the total phase drop is 270 degree from low frequency to very high frequency. So in order to compensate this loop, one idea is using an integrator. And with that, I can add more DC gain at low frequency. And then because integrator has one pole at origin at zero frequency, it drops the gain. And I can adjust the point that this magnitude transfer function crosses the 0 dB line, and we can, by changing the gain of the integrator, I can adjust this crossover frequency to a point that my phase uh, has enough margin from 180 degree, which is the edge of instability. So this is what's done in the compensator design. I'm assuming a compensator with a transfer function of 10 over S, which is basically an integrator. The value of 10 is adjusted such that the crossover frequency of the loop, this point, is around 160 Hz, which is a very low bandwidth, but at this point, my phase reads about just below 90 degree away from 180 degree phase margin, so I have 89 degree phase margin, and loop is stable. In fact, this loop behaves as a first order system because our phase margin is very close to 90 degree. Then after crossover frequency, my magnitude drops, and although we have this magnitude peaking from conjugate pole, we still have some gain margin, so it's still way below 0 dB. So this means this loop is properly stabilized. But the question is the bandwidth of 160 Hz enough for good transient performance? Probably not. This is way too slow. So there are other ways of compensating this loop that allow us to push this crossover frequency and loop bandwidth to higher frequencies. So you will look at the same example in the buck converter compensator design in your problem set, and you can find more complicated compensator, but the idea is very similar. We just look at the Bode plot and try to adjust the compensator parameter for the fastest bandwidth while having a good phase and gain margin. So in summary, today I covered the behavior of an inductive boost converter both in steady state and also in transient. We saw that inductor volt-second and capacitor charge equations can be used to understand both steady state and dynamic behavior. We also calculated the load currents that correspond to threshold or boundary between continuous conduction mode and discontinuous conduction mode. It's very important to understand where the converter enters discontinuous conduction mode, mainly because of very different steady state and dynamic behavior in that mode. And lastly, in a closed loop converter, we need a compensator to shape the closed loop transfer function to meet our steady state and transient design requirements. Thank you. I hope you find this problem session material helpful.